There you go.
Okay, guys, so we should get started. I've been asked to remind everybody to sign in if you got pizza. So that's me asking you guys to sign in if you got pizza. So today we have Christian Reichardt, who is a good friend and a close collaborator. Christian just reminded me I've known him actually since 2000. Actually, since 2000 when I came to Caltech. You were a junior, I think. Then. Christian's a remarkably productive scientist. He's been working for a relatively short amount of time. And you may not know this, but you've heard of the H-index, right? Mm-hmm. So the H-index was invented by our colleague here, Jorge Hirsch, who's a physics professor. H is after him. But I've recently, after looking at your publications on Google Scholar, come up with a new index called the age-index, which is what is your age relative to your age, divided by your age.
That's
the end
That's a thing. Yeah.
That is a thing? What? You stole my idea?
Any did the
I knew that satellite was... All right, so Christian has an age H-index of 1, basically, which is to say his H-index is over 30, and it's quite remarkable for such a young scholar in the field. And a lot of that's attributed to publications that he's led the work for. So in particular, the Akbar experiment, which is a PhD thesis. He got his PhD in 2008. That's right, 2008, working on the Akbar experiment, which until very recently had the. You guys missed my introduction of a statistic called the age index, which has already been co-opted by somebody else called the M index. Sorry. So Christian worked on the Akbar experiment and deployed to the South Pole to deploy the hardware that he had worked on while he was a grad student for Akbar in 2005. So he's been to the South Pole and yet returned to tell the tale about it. So today he's going to talk about an experiment that's currently going on at the South Pole, which is a sort of a competitor to polar bear, but also he's a collaborator on polar bear. So he's kind of in the catbird seat. He gets to work on 2 exciting experiments at the same time. And really what he's trying to do, as he says in his title, is probing fundamental physics, which is to say we're now probing what I consider the 4th most important particle in all of physics. George considers it the most important particle in physics, namely the neutrino mass. I mean, imagine if we didn't know the mass of the proton, the electron. So Christian's going after probing aspects of fundamental physicists, heretofore reserved for our high-energy colleagues who are now coming down because they smell pizza all the way from there. So it's a pleasure to have Christian. He's visiting today and tomorrow. We have spots for dinner available if people are interested, and lunch tomorrow. So please contact me if you're not on the list to meet with him. And otherwise, we're going to hear about this exciting new physics being probed by 2 of Christian's experimental projects.
Thank you, Brian. So as Brian said, I first went down to South Pole back in 2004, and I saw the foundations of the South Pole Telescope starting to be built, the ice foundation for this. And I've been fortunate enough to work on it as my main focus while at UC Berkeley. During the course of the talk, I'll begin with a brief introduction and review of cosmology. Use this to motivate why we built the South Pole Telescope survey, as well as the polar bear surveys, and what we are finding in these surveys. From there, I'll focus in on the power spectrum of the cosmic microwave background, which is the normal way we have to interpret the data for these surveys, and talk about the features in the power spectrum and the cosmological interpretation thereof. And in particular, I'll be looking at what we can learn about inflation from the cosmic microwave background. And then I'll transition from data that we have to data that we're taking with CMB polarization, which can tell us both about inflation, but also about gravitational lensing of the cosmic microwave background, which gives us a handle on structure growth and the masses of neutrinos, as Brian mentioned. And I'll be talking about 2 experiments on the sky right now, SPT-FOL and polar bear, and their planned successors, SPT-3G and the Simons array. So the current model of cosmology right now is lambda CDM, lambda for a cosmological constant, CDM for cold dark matter. It's a fairly simple model in terms of the number of parameters. You have 6 free parameters. Yet this model can actually explain all the observations we have today, ranging from the temperature and polarization anisotropies in the cosmic microwave background to the distribution and number counts of galaxies or galaxy clusters on the sky, to measurements of the geometry of the universe, such as the luminosity-distance relationship from supernova. At this point, we have, of course, thousands of data points constraining the 6-parameter model, so we have very tight constraints on our model parameters, pinpoint down a very tiny region of space, and we've learned that we live in a flat universe. The initial perturbations are
Mm-hmm.
nearly Gaussian and scale invariant. And the expansion of the universe is actually accelerating today, somewhat counterintuitive. And this points to one of the interesting aspects of this model. Although it's very simple, a lot of the major points of the model are still not very well understood. So 95% of the universe's energy density there is composed in the dark sector of dark matter and dark energy. And of course, their very name encapsulates how little we understand about what these objects actually are. In addition, we typically invoke a period of superluminal expansion early on, inflation, to address, for instance, the horizon problem. However, we don't know what causes this rapid expansion in the early universe. So all three of these are pointing to physics beyond the standard model that we could understand by studying cosmology. To understand how you might learn about these, it's useful to look at how the universe evolves in the standard model cosmology. This is a pictorial representation of the history of the universe that you've likely seen before. And loosely speaking, you can break down the history into sort of 5 epochs: inflation, the early hot plasma, reionization, the structure formation, and the accelerated expansion. What's nice is that my work relates to each one of these different epochs. On the following slides, I'll go through these in a little more detail and highlight some of the questions that remain about each epoch. We start off with inflation, in which you have this sort of e⁻⁶ expansion of the universe. This addresses problems ranging from the phase coherence of the CMB to the horizon problem to why we don't see magnetic monopoles. However, it's a big black box. We don't know what energy scale this physics comes into play, and we don't really know what is driving this rapid expansion, and whether there's any connection to the late-time acceleration in the late-time universe. After inflation, we have a fairly good idea of how a hot plasma will evolve. As the universe expands, this plasma cools off, and different particle species can fall out of thermal equilibrium and survive at some relative particle abundance. Eventually, you cool down sufficiently that your protons and electrons combine to form neutral hydrogen, and the cross-section between free electrons versus neutral hydrogen is much higher, so now the photons can escape to free stream all the way to the observed space. We get a snapshot of what the universe looks like a few 100,000 years after the Big Bang in the cosmic magnetic background. This is our first image of the universe with electromagnetic radiation. In post-Planck era, you can learn more by studying polarization and smaller scale anisotropy to learn both about the initial conditions and about inflation thereby, as well as particle physics in the early universe, like decaying dark matter, neutrinos, and other extensions to the standard model. After the last scattering, you have a fairly neutral sea of hydrogen. But eventually, under gravity, these form the first stars and then the first galaxies, which produce UV and X-ray photons that should reionize the universe around it. And we know that by a redshift of 6 or so, the universe has reionized. But we don't really know what sources cause this reionization, what kind of stars, what kind of galaxies, and in fact, whether ordinary stars and galaxies are sufficient or whether there's something more exotic going on to drive the reionization process. This has, of course, been a major focus of 21 centimeter surveys, and we'd like to understand this in more detail. Structure continues to form in the ionized universe, and by studying this process, you can learn about dark matter, which is driving much of the structure growth. And this is forming under gravitational infall to form larger and larger structures in a bottom-up model. And by studying the process of structure growth, you can learn not only about dark matter, but also other properties like the masses of neutrinos. Since neutrinos act like a form of hot dark matter that delays structure growth on the smaller angular scales. And the last half of the universe lifetime or so, below redshift of 1, instead of being a matter-dominated universe, we transition to being a dark energy-dominated universe, and the expansion of the universe begins to accelerate. This was first discovered by supernova, but has since been observationally confirmed by a number of other measurements, from variance oscillations to CMB lensing. But we don't know what is causing this acceleration. And it could be a breakdown of general relativity on cosmological distance scales, it could be a dynamical dark energy model, or it could be the cosmological constant that Einstein had proposed. And any one of these would be very interesting in physics. The nice part about doing a small-scale cosmic background survey is that you can actually touch upon all of these different epochs. So, of course, you get a snapshot of the early universe, which can tell you about those initial conditions, inflation, and particle physics in the early hot universe. But these CMB photons have traveled through the entire universe, and they bear some small imprint of all the structure along those lines of sight. There's two main effects. There's the Sunyaev-Zadowicz signal, in which you have constant scattering between free electrons and the CMB photons. And there's gravitational lensing, in which the path of your photons is bent by structure along that line of sight. And these two effects give you sensitivity anything from the epic radiation to the dark energy for, say, looking for galaxy clusters you see at the dose range. In this talk, I'm going to be focusing on these two questions, what causes inflation, and what we can say about neutrino masses from gravitational lensing. To do this science, we built the South Pole Telescope, which is a 10-meter telescope located at our best known millimeter wave observation site. To understand why the South Pole is such a great site for millimeter wave observations, it's useful to know what an atmosphere emits at these waves. That's water vapor. Water vapor is not very well mixed in the atmosphere, so it leads to a time-varying signal depending on how these clouds are blowing in front of your telescope. And the best way to get rid of water vapor is to go to someplace that's really, really cold. And the coldest temperature every winter at the South Pole is actually below the sublimation point of dry ice at sea level. So it's really cold at the South Pole. And that means we have very little water vapor in the atmosphere, so we have a very clean atmospheric signal to look for. In addition, you can see a very clean patch of extragalactic sky that allows you to do very deep CMB maps. We also have a state-of-the-art telescope. 10 meters gives you an arc-minute resolution on the sky, which is well matched to, say, a galaxy cluster size. It's designed for surveys. You can scan quickly, 2 degrees per second azimuth, with about a 1 square degree field of view right now. This is a picture of the collaboration at our last collaboration meeting in Chicago, around 50 people. This metal piece actually is part of the telescope that we had to replace, the AS bearing, in 2009, because it broke and we had to put in a new one. We've put 3 receivers on the telescope so far. The first one, SBT-SC, is the one that you've probably seen the most science results from with this telescope. SBT-POL is observing right now, and SBT-3G is planned to observe in a couple of years. Now, SBT-SC was built at the UC Berkeley nanofab facility, has about 1,000 detectors, and each one of these triangles here is a single frequency, potentially. Those are different filtered frequencies. 4 of these triangles are at 150 gigahertz, which is our main science band, and then 1 each at 95 and 220 gigahertz. So we get down to the noise levels you can see here across 2,500 square degrees, which is about 6% of the night sky. And to interpret this noise level, if you break down this 2,500 square degree map into 1 arc minute by 1 arc minute pixels, the RMS across those pixels would be 18 microkelvin at 150 gigahertz. Now, we put a new receiver on this telescope in 2012. This had 2 main advantages over the first receiver. We changed to a polarization-sensitive detectors, so we can go after CMB polarization. And we have 50% more detectors for better mapping speed. Since we're going for CMB polarization, which is a fainter signal, we are targeting a smaller patch of sky, but to much lower noise levels, about 4 times lower noise on 4 times smaller area of sky. And we're currently planning the third receiver, SBT-3G, which we're going to increase the detector count by a factor of 10, so a tremendous factor. And we're getting this increase in detector count in 2 ways. First of all, we're redesigning the optics. The secondary mirror is being replaced, as well as the lens system, to expand the real estate on the focal plane by a factor of 3. And second of all, instead of going with these feed horn coupled single frequency pixels, we're going to broadband seamless wave antennas coupled with lenses to the sky. We're going to get 3 pixels off every, or 3 frequencies off every pixel on the sky. And with this camera, we're going to survey, again, 2,500 square degrees down to ultra low noise levels, 2.5 microkelvin arc minutes at 150 gigahertz. But to return to what we have right now, this is the current survey in all its glory, 2,500 degrees, also shown here on the all-sky globe to give you a sense of where it is on the sky. This is, of course, a smaller patch of sky than a satellite experiment like WMAP or Planck, but we're much lower noise with much better resolution on the sky. So some variation on deepest times area you can get. This is the deepest, largest area map. Compared to WMAP, our beam size is 13 times smaller, and our noise levels are about 17 times lower than WMAP. And compared to Planck, WMAP's successor, we still have a beam size that's 6 times smaller than Planck, and our noise levels are 2.5 times lower noise. So we have better resolution and much lower noise than the satellite experiment. And part of that's just that it's much easier to have a large telescope on the ground than it is to launch it into space.
Sorry, can I ask a dumb question?
Mm-hmm.
How much are these pictures that we usually see are raw, and how much processing goes on top of this to actually come to this picture? I mean, is this the raw picture? This is how it looks? How much filtering? How much?
This is fairly lightly filtered because we want to recover the large scales. For most of our science, we filter it more heavily because we don't actually care about recovering the scales that you're seeing here.
What goes into this? What goes into this? Because I never know, and it's never decided.
So we have, some data quality selection, where we throw away bad data, where we either don't have calibration, or you see, say, a cosmic ray, or some other event in your data. And then for this map, it's virtually, I think we removed like a mean from each one of our scans, and then just binned it up into the map. This is a very lightly processed filter for this map. More typically, we do more filtering. We remove common mode across our array, which is basically atmospheric noise blowing through. That's our main filtering. And for polarization, sometimes we difference the two polarizations in the pixel, again to remove atmospheric noise on these large scales.
And what's the dynamic range of the vertical scale? What is the different colors in 7?
This is about plus or minus 200 microkelvin.
What does it tell you?
It's a measurement of the temperature.
Yes.
How much the temperature is varying across the sky. So it's a 200 microkelvin temperature variation, plus or minus. So it's around a range of 400 microkelvin from the darkest blue to the white.
And it's basically at 3 fixed frequencies, you just measure intensity.
This is only one frequency map.
So you have 3 such maps, if I understood you.
We have 3 such maps, yes. This is 90 gigahertz, which is the easiest one to recover the large scales on. And for the very large scales, you don't really care about the multi frequency is more important for the small scale information than the large scale information. Because on large scales, the CMB has basically a perfect black body. So we know how to, there's no frequency information to use there. Okay. To give you a better sense of how this compares to the satellites, I'll zoom in to now 5 degree by 6 degree patch sky, roughly 30 square degrees, where you can see the effects of having a smaller beam and lower noise more accurately. This is what this patch sky looks like with WMAP. You can see the very large scale temperature anisotropies in the CMB here. If you fast forward, this is what happens when you go from WMAP to Planck. You now start to see smaller scale variations in the temperature distribution on the sky. And this is what happens when you fast forward to SBT pole. Now you're actually seeing these, for the first time you start seeing features besides the cosmic microwave background in your maps, as well as seeing very small scale anisotropies.
Those are quasars, whatever.
Yeah, I'll talk about the next slide. So the bright spots are, as you say, the very bright ones tend to be radio sources, synchron emissions from like AGN or quasars. They dominate our bright source count. The size of these dots is not the size of the quasar, but it's the size of our revolution on the sky, I should say. As you go to the dimmer side, some of these are actually become dusty galaxies, so high redshift dusty star-forming galaxies. And we are seeing the very high flux ends. These tend to be strongly lensed versions of them. We're talking about 10 milligencies, 20 milligencies objects. And about more than 50 of these have now been followed up with ALMA to look in more detail at the lens and galaxy model. But I won't be talking about these in this talk. You can also see some dark spots in this map, quite distinct from the white spots. And these are galaxy clusters. Effectively, these are shadows where we get fewer photons along that line of sight from the surface of last scattered. And these are interesting for studying dark energy. They're pretty easy to find with this resolution because they have a very characteristic signature. They're very small compared to the temperature anisotropies, and they're negative rather than positive like the galaxies would be. Now, these are the most massive objects in the universe, and just they are very rare.
My question.
Yes?
How much of the improvement was from the better beam size versus how much from the noise?
It would depend on which science field you're talking about.
Okay.
For something like galaxy clusters, the beam size is very important. For something like polarization of the CMB, the noise is more important. So galaxy clusters are very large, the most massive collapsed objects in the universe. And the key part for us is that although they contain a lot of galaxies, most of the ordinary baryonic matter in galaxy cluster isn't in the galaxies, but in the intercluster medium. And this falls into that massive potential and gets heated up to 10 or even 100 million Kelvin and forms a diffuse hot plasma. And with this diffuse hot plasma, of course, you get thermal Bremsstrahlung emission, which shows up in X-ray, and this purple coloration on top of the Hubble image is the X-ray from Chandra, image of that galaxy cluster. But this also means that if you have a CMB photon passing through this galaxy cluster and you have a scattering event, the CMB photon is only a few Kelvin. The electrons, tens of millions of Kelvin, so the photon gains energy on average, and it's kicked up to higher frequencies out of our observing range. So we see fewer photons along the line of sight to a galaxy cluster. It's a nice way to detect these galaxy clusters because the brightness is independent of redshift. So you can detect them out to the redshift of formation. And counting these galaxy clusters is interesting because their number count is quite sensitive to the properties of dark energy or neutrino masses and other parameters. We find that a lot of these objects, this is just a sampling of the first 780 square degrees of our survey, snapshots on detected galaxy clusters above 5 sigma. We expect on the order of 600 objects within the full survey, and that catalog is being produced right now. And we have around 200 confirmed galaxy clusters published so far. And we'll do even better when you look at the SBT3G and SBT pole. What's nice about this is that we actually get comparable constraints from galaxy cluster number counts as you do from, say, supernova in terms of constraining the properties of dark energy. And there are quite different probes of what we're looking at. Because now we're looking at structural growth instead of geometry. And by comparing structural growth and geometry, you can help distinguish between dark energy versus modified gravity in those two different paradigms for what's causing acceleration. But for the rest of this talk, we'll be talking about everything else in this map, which is the cosmic microwave background photons coming from the surface of black scattering. And the typical way to discuss these is by looking at its power spectrum, because this is a nice way to compress information in that map into a much more easily manageable data set. And since these are basically Gaussian perturbations, we don't lose any information in this process. And additionally, we can predict the power spectrum quite well for any given model. So there's a very tight link between what we're observing and what the theoretical predictions are, which gives you very strong constraints on cosmology. And this has motivated strong experimental progress. So the cosmic microwave background was discovered back in 1965 by Penzias and Wilson. It took 27 years to actually discover any anisotropes in it, and that happened in 1992 with COBE. But 10 years later, we've now gone from measurements at L30 or so all the way up to L3000. So a factor of 100 in English scales probed in the 10 years after the first detection. And now, of course, you had the first Squeeze peak, as well as the damping of the CMB. 5 years later, WMAP has come on the scene. This is the second data release of WMAP. Boomerang, balloon experiment, and Akbar Matisse experiment out through the damping tail. And about a year ago, this is where we were with the last release of WMAP and the full survey, SBT survey. At this point, we've now gone forward to 9 acoustic peaks in the power spectrum with the data. And just to flip through this again to highlight that progress over the last few years,
Do you count that as 9 peaks now or 8 peaks?
That's depending on how you want to count it. That's their argument. We have not.
Where their particle physics
Yeah. So we've gone from here to here to here. So there's been tremendous progress in the last decade in this field.
Are you going to show the polarization peaks in EMO?
I would not actually show the polarization peaks, because then you'd have more.
But there's 4 peaks to check for polarization. Okay, sorry.
But to better show the small scale feature, I'm now going to show you a plot with the y-axis multiplied by the x-axis squared to tilt that up. That is what we're showing here. And now you can actually, this is the second acoustic peak, third, fourth, fifth, sixth, seventh, eighth, and then depending on what you count, ninth acoustic peak in the power spectrum. This plot also shows you the comparison of what the South telescope band powers did compared to other data that was out there. So we also had Akbar and ACT, which was the telescope in Chile, as the main competitors on these small scales before Planck. And compared to either one of these comparison, South telescope band powers improved this measurement by a factor of 3 across this entire angular range. Now, in spring of 2013, this last year, Planck came out, and compared to Planck, basically the South Pole telescope transitions around L of 1800, to where the Planck dataset is better at larger scales, and the SPT dataset is better on smaller scales. This is just a comparison of all these datasets right now for our best measurement. Now, if you want to look at what we're looking at here and why we have single frequency band powers down here and several frequencies out here, it's useful to understand what we're looking at. So on this range of the power spectrum, we're looking basically at classic cosmic microwave background. We have basically a perfect black body dominated by the photons from that surface of black scattering. And as you go to the smaller angular scales, you now begin to be dominated by interactions between those cosmic micro-background photons and large-scale structure, as well as foreground sources like the radio galaxies or dusty galaxies. And for those purposes, it's useful to have multi-frequency information to disentangle the different possible signals. And that can be interesting for doing, say, measurements of the kinetic of the Doge effect and learning about the ionization history of the universe. But for most of this talk, I'll be talking about this classic CMB. We're in the process of improving these measurements, I should say, with a paper led by Elizabeth George, who's a graduate student at Berkeley I'm supervising. And she just graduated, so this paper should be out pretty soon. And starting out, the transition point from where Planck does a better job and goes all the way out to L11,000. I'm only showing out to 10,000 to match the previous plot. And these errors are a factor of 2 improvement over what we have right now in the data set. I'll now transition to talking about cosmological interpretation of these band pairs and focusing on the causes of inflation. So the peaks that you're seeing in this power spectrum are caused by acoustic oscillations in that early hot plasma. Effectively, the idea is that as the universe expands from the beginning, larger and larger modes enter the horizon and begin to evolve. So let's say our mode sees the dark matter overdensity and begins to fall in it. You see your first acoustic peak when it's had just enough time to hit maximum compression, and then pressure kicks it back out. You get second acoustic peak when it's at maximum rarefication and a cold spot on the sky. So the peaks are alternating between compressions and rarefications into those dark matter overdensities. And what you measure best in terms of distance scales in this power spectrum, therefore, is actually the sound horizon scale at the source of last scattering. Effectively, if we measure 9 acoustic peaks, we gain 9 measurements of what that sound horizon is. And the angular size, which we measure angles on the sides, we also have a measurement of the angular diameter distance to the source of last scattering. This is also the same sound scale that used in, say, baryon acoustic oscillations in the low redshift universe, just at a much different redshift scale. A second distance scale in your problem is the damping scale, which is why power is dropping off as you go to smaller scales. This is basically a measurement of what the mean free path is of the photons in that early hot plasma. And since they are going to diffuse out of small scale anisotropies, the perturbations will be damped as you go to smaller scales. In addition to those 2 distance scales in the problem, you have information about the acoustic peaks. So for instance, by looking at the even versus odd acoustic peaks, you're looking at compressions in phase or out of phase with the dark matter, and you can learn about the ratio of baryons to dark matter. A key point in looking at this is that all the current CMB power spectrum, including the South Pole telescope, are in good agreement with a 6-parameter lambda CM model. The PTE for our data set is about 21% for the best fit model of 6 parameters. So there's no real tension with the model. And actually, it turns out that with these data sets, was now the first time which actually were getting comparable constraints from the damping scale physics that you were getting from the first acoustic peaks on the 6 lambda CM parameters compared to WMAP. So by combining SBT data with WMAP, we got about a square root of 2 improvement on the constraints in those 6 parameters. But where you really shine for doing a small scale ground experiment is when you start looking at extensions to the standard model, which can then affect the ratio of that damping distance to the sound horizon scale. And we'll now transition to talking about that and looking at the initial conditions of inflation and what caused inflation. So there are generally 3 types of perturbations that you might consider in your model. First of all, of course, there has to be density fluctuations because we exist and we're the product of density fluctuations that have grown with time to form planets and stars. These are the only perturbations that are growing with gravity in this expanding universe, so they're very important. In addition to those density perturbations, you can have potentially vector perturbations, which would be effectively eddies in your matter distribution. However, these vector perturbations are exponentially damped in an expanding universe, so they are generally negligible within inflationary models, and I'm going to ignore them for this talk. And then finally, you can have tensor perturbations, which are gravity waves. And generally, since inflation has this very rapid stretching of space-time in the early universe, it predicts some background of these gravity waves that you can detect on cosmological distance scales. And the amplitude of the gravity wave background relates to how rapidly the universe is expanding, and thus the energy scale, which is physics, comes into play. Conventionally, you express the amplitude of your gravity wave background by a parameter r, which is the ratio of the tensor scalars. However, at this point, we've actually constrained the scalar amplitude quite well, so to a very good approximation, r can be viewed just as the amplitude of the gravity waves times some fixed prefactor.
Do the vector perturbations produce significant temperature power?
I think it produced basically, I think it would produce a lot of B-mode power, if I remember right.
Right. So they could produce B modes, but not temperature.
I don't think they did that. I mean, yeah, they produced some temperature, but I don't remember how much. But my recollection is they'd be the ones that produce more B-mode. Actually, no, yeah, they only produce B-modes. I think you're right that there's not significant temperature. One of the predictions of inflation is that the power spectrum of your initial perturbations at the end of inflation should be nearly scale invariant. This is related to the fact that inflation is a nearly time invariant process. It doesn't really matter at what time a mode enters the horizon. However, since inflation ends, it's not perfectly time invariant, and therefore you expect some small deviation away from scale invariance. Now, if we express our power spectrum as this frequency up to a power law, n spec minus 1, n spec equals 1 will be scale invariant. And if you change n to s, this will lead to this impact on your temperature anisotropy. Effectively, you're tilting your power spectrum, and adding small scale data is useful because, of course, you're measuring a longer lever arm to measure what n sub s is. And indeed, by adding the small scale CMB data, we get very significant detections now of a departure from scale invariance. With WMAP, we had around 2 sigma. By adding that South Pole telescope data, you can bring this up to about 4 sigma, 3.9 sigma. And Planck raised this up to about 5 sigma, and Planck plus SBT, which is another small scale covariant DO, brings it up to around 7 sigma. So the small scale CMB data, even with Planck, is improving the measurement by a factor of 1.4. This is now a very significant detection of a departure from scale invariance, matching that prediction of the inflationary model. Now, looking at gravity waves, the other parameter we talked about, gravity waves decay in an expanding universe. So you see the largest impact on scales that were larger than the horizon at the last scattering surface. So very large scales. And these values of R range from no gravity waves to equal power in gravity waves on these large scales that you have in the scalar mode. And you can say that even if it's equal power at large scales by L of 100, which is a couple of degrees, on the sky, it's virtually no impact. Now, since SPT band powers don't start to L of 600, another factor of 6 smaller, you might ask, why does the small scale data actually help you on gravity waves? And the answer comes in the fact that we're not only varying the gravity wave background, of course. We have at least 6 other parameters in your model or more, depending on how many free parameters you want to introduce here. And over this range, this change in tilt can, for instance, be mimicked by another parameter like n sub s. So if you, for instance, look at the best fit model for different values of the gravity wave background, with the WMAP data alone, we get good fits for the WMAP large scale range, but then disagreement on smaller scales due to how these degeneracies with the other parameters that you're adjusting to match the large scale data. And I should note here that I've once again multiplied my y-axis by the x-axis squared to highlight the small scale shifts. These shifts are small, but they're about the size of the error bar for the South Pole telescope data. So we can break those degeneracies. In fact, we do. By combining WMAP plus South Pole telescope data, we get the best limits that we have right now on the tensor to scalar ratio, so on the gravity wave background. And we get limits when combining the CMB plus beta crystal oscillation data at 95% confidence that R is less than 0.11. This actually is about the fundamental limit for how well you can do from temperature data. If you calculate in a model where you only vary R, you fix all your other parameters, and you find that about 50% of cosmologies, your 95% limit on R would be R less than 0.1. So we're right up against the theoretical limits due to the limited number of modes on these large scales that you can get from the temperature data right now. And in fact, if you look at Planck's constraints, they're basically the same for that reason. In the future, you can do better with polarization, as I'll talk about in a few slides. But you can already actually start to put constraints on some common inflationary models with the current data. And these are 1 and 2 sigma colored contrast for WMAP plus SPT, and all of the above. So let's focus on the blue curve here. And for a given form for the inflaton potential, you can generally predict what the predicted values of both n sub s and R for the inflaton potential. So if you have an exponential form for your inflaton potential, you'll fall somewhere along this line. And you can see these forms of inflaton potential are now disfavored at more than 2 sigma with that current data set. Similarly, you can look at chaotic field inflation models, which are impound potential is power law, which you predict depending on how many e-photons are during inflation, you predict values that say look like this. And again, these are for high values of the exponent ruled out at several sigma with the current data. As you go towards small field models of inflation, like the hilltop model of inflation, it actually is consistent with the data. And to start to look into the small field inflation models, we'll have to move forward to use CMB polarization. Before I get there, I'll just note that Planck data, as I mentioned, is consistent in the allowed parameter ranges of NSS and R, and with also consistent error bars with their data sets. To improve upon these plots, we're looking forward to polarization, as I mentioned. So we can improve the x-axis, the constraint on the slope, n sub s, by about a factor of 4 from a combination of Planck plus SPT3G. Most of this improvement will come from Planck polarization data that is supposed to be coming out in the next year or two. That'll be about a factor of 3 of this. About the remaining 30% will be coming from even smaller scales that you can get from the ground-based polarization. And then there's a larger impact for the ground on the gravity wave background R, where you don't have the same confusion noise as you do in temperature. And something like the Simon's array is predicting order of magnitude improvement in our constraint on the gravity wave background. So R, currently we're talking about sigma R of 0.055 and going down to sigma R of 0.005.
Of course, once you realize that there was not a limit.
It could be, but who knows. These are not yet the fundamental limits for how well you could do in the CMB. The fundamental limits for measuring R in CMB, depending on who you ask, are somewhere in the order of 10 to the minus 4 to 10 to the minus 5. So there's another factor of 50 to 500 that you could do with future CMB polarization experiments with better detectors and lower noise levels, depending on how far you want to de-lens and what angular scales in the sky you're willing to use. And I'll now transition from sort of the power spectrum, talking about some of the other future improvements that we can get with CMB polarization. And in particular, I'll be talking about gravitational lensing of the CMB and how we can use this to learn about high rates of structure growth and the masses of the neutrino species. So to understand lensing, let's just look at what an unlensed CMB map looks like. This is 15 degrees by 15 degrees on a side. And this is what happens after you lens that area of sky. So you've probably seen a small shift between the two. You can pick up by eye. It's still small, but our current experiments are quite sensitive, so we can detect these kinds of deflections. To better view it, we can look at the difference map between these images. And as you can see, the actual individual deflections are an order of arc minutes. I think 2.5 arc minutes RMS. These are in the weak field deflection limit, so each one of these observed deflections is product of, say, 50 individual deflection events along that line of sight. And although these are small, they're coherent on large scales. So they're coherent over many, even tens of degrees. So you want a combination of both small-scale information and large-scale surveys. You can then use this deflection field to reconstruct the integrated matter potential along that line of sight and give you a map of all mass in the universe along those lines of sight. Now, people are, of course, also talking about doing weak lensing surveys in optical. The CMB has a couple of differences compared to optical weak lensing surveys. One notable difference is that the raw signal noise is lower. However, our systematic control is much better. So it's very clean systematic because we have a very well understood source spectrum. People have studied the potential polarization anisotropies. They're Gaussian. They have a well understood shape distribution on the sky. And all of our photons are coming from Z of 1100. So there's no biases due to what redshift their source galaxies are at. It gives you a very clean systematic form. In addition to that, the second advantage beyond systematic is just the redshift range of gravitational lensing. These are our highest redshift photons, so it's the only game in town if you want to do weak lensing at a redshift of couple, redshift of 4. The CMB is the only way you can do it because there aren't enough otherwise background galaxies behind it. And the redshift kernel for where most of the lensing power is coming from is somewhere between a redshift of 0.5 up to a redshift of 4 or so. And using this, you can then actually, as I mentioned, make a map of all the mass in the universe on your patch of sky. This is an analysis of SPTSC data being led by Oliver, which I'm working on the simulations with for understanding what our transfer functions. And it's a mapping of 6% of the mass in the universe over the 6% of the sky. Now, this is a smaller area than the Planck satellite lensing maps, but we have higher signal to noise per mode. This signal to noise is greater than 1 on these large scales. It's a realistic reproduction of what the mass distribution is. This is a sort of estimated total signal noise, 20 sigma FT versus the all sky 30 sigma. It's worth noting that these are very complementary. About 75% of the SPT signal to noise is coming from smaller scales than Planck has published. So it's a very different range of angular scales where we're getting our information compared to Planck. They aren't duplicating the same information.
If I take a random block there, it's pretty sure that that's signal and not noise, or is there a mixture of signal and noise there?
The signal to noise is on the order of 2 or 1.5. So it's not.
So
There is noise in
some
there.
blobs in there that are just noise.
There are some blobs in there that are.
And how uniform is your transfer? Is a Monte Carlo transfer function?
Hmm?
How uniform is the Monte Carlo transfer function?
It varies a little bit between fields. This is a stitching together of different, 20 fields.
How big is the correction?
It depends on what L scale you're talking about. It's normally around the peak is several percent, but on the
So it's a few
very
percent.
large scales it can be larger.
It's a few percent to how many?
Up to infinite. At some point our high pass filter just kills all signal. We have a band pass filter effectively in our map making. So if you go far enough to large or small scales, we don't have any information.
Sorry, this is an integrated mass from redshift 0 out to the redshift infinity.
Yes.
And your beam size is much smaller than the size of one of the
Yes.
blobs. So the ones that are real and not noise, are these it's like the size of what, superclusters or filaments or what?
Well, this is how you know. Yeah.
It's not individual clusters.
No, these are way larger than individual
Yeah.
clusters.
These
These are
have to be like giant.
100 megaparsec type scales.
Super duper.
Super duper. These are 100 megaparsecs and beyond.
Yeah.
But this is like a WMF beach ball, but it's you're looking at dark.
Yeah, I know. It's
Right.
cool.
Yeah.
It's all nearby stuff too. It's not out
Yeah.
of redshift.
Yeah.
That's what I was wondering, because it doesn't look like
I
the
guess-
cosmic web that we normally see.
Yeah, I guess the question would be like, what scale? Because I'm just not used to thinking about these big scales. Like the Sloan Great Wall would be how big on this scale?
How big is the Sloan Great Wall?
It's up to 8 degrees one way, 8 to 10 degrees.
Those are,
That's so
those are
close.
50
Yeah.
degree longitudes.
Yeah, these are. Yeah, so if there's 8 degrees, you can do like that.
Okay. Cool.
So this is with temperature data where you have to average over many blobs to reconstruct the lensing. You can do much better if you go to polarization, get much higher signal to noise. Now, polarization is basically a vector field on the sky. And one way to decompose the vector field is into modes that have gradients but no curl, analogous to electric fields, and modes that have curl but no gradients, analogous to magnetic fields. We call this E and B. And the reason we tend to use this decomposition in cosmology is that those density fluctuations that we talked about, scalar perturbations, are not producing any B modes for symmetry reasons. And that means there's no confusion noise if you look at the B modes for understanding either gravity waves or gravitational lensing. And gravity waves produce B modes on very large, several degree scales, which can tell you about the gravity wave background from inflation. And as you go to arc-minute scales, you're learning about gravitational lensing of the CMB. And you can distinguish between these two effects based on what angular scales you're looking at. To illustrate, now with both polar bear or SPT, we have relatively small beams, so they're very good at doing gravitational lensing. And to illustrate the impact of lensing on these different power spectrum, we have both lens and unlensed power spectrum for the 10 transatopes. The changes are quite small. The E-mode polarization atopes, again, the changes are quite small. And when you go to the B-mode power spectrum, now you get 2 orders of magnitude shift in your observed B modes based on gravitational lensing. So if you can measure these B modes, you can get a very high signal-to-noise measurement of this lensing map on the sky. Of course, this plot also illustrates the challenge, which is, of course, that these B modes are quite faint compared to the anisotropes that we've been talking about so far. So you need very good instruments to get down to these low noise levels. Now, one thing you can do by looking at the distribution of mass on the sky at high redshift is to probe the masses of neutrinos. Adding mass, changing mass from dark matter into neutrino mass tends to increase the occurrence rate in the local universe, which delays structural growth.
Sorry,
And-
Christian, what's called lensing B modes to peak of reionization? Peak. The lensing B mode, why is that traced by reionization if the E modes aren't?
This is full.
That's total.
This is total.
Okay.
But
it's
the
not-
difference is lensing.
Right. So okay.
Yeah, this is the total. but except for that small radius, it's all white. Effectively. Okay, yes. So
I have another dumb question on the previous slide. So does this mean that you have to, in order to actually get the inflation B modes, you have to have made a map of the matter in the first place? Because otherwise you can't subtract out the lensing B mode?
It depends on how bright the gravity waves are. I think below an R of on the order of 0.01, so 10 times lower than the current limits, you would start to have to worry about subtracting out the lensing B modes. But if it's within above that, you won't have to. You can just do it by only looking at the very large scales, and it'll be dominant on those large scales.
So in other words, on the left of this plot, I don't have to subtract anywhere above 500 or so. I would have to subtract.
Well, actually, it's pretty much L of 100 is where you're seeing the gravity wave background. So, if it's this plot, it's hard to see.
Oh, this is a log scale on the y-axis.
Yeah, it's a log scale on the y-axis. So so if you change dark matter into neutrinos, adding neutrino mass, you increase the expansion rate today, which slows down structure growth, since it's harder for that structure to exceed the expansion rate and start to collapse. And this leads to a suppression of structure growth on small scales by an amount that's just proportional to the total neutrino mass. And this leads to, these are some of the best constraints we have right now on neutrino masses. As you go to larger scales, then these massive neutrinos do start to cluster as well, which enhances structural growth, and basically cancels out that factor expansion rate, so you have no changes on very large scales. And where the kink is will depend on the individual masses of the neutrino species. The key part for what we were just talking about is basically 100 milli-electron volts of neutrino mass will change the BB power spectrum by 5%, to give you an idea of the size of the effect. I'm involved with 2 experiments that are on the sky right now that are going for these science goals. This, of course, is SPT POL, the polarized camera on the South Pole Telescope, and Polar Bear, which, of course, Brian and other people in this room are working on as well. But it's something of a coincidence that both of these experiments actually had first light in the same month, January 2012, and they're pretty similar, actually, in terms of their mapping speed and sensitivities of the both. They each have around 1,500 detectors with similar mapping speeds on the sky. However, they're quite different in terms of their ability, their technologies, and systematic control techniques. So here we have these feed horns. Here we have dipole antennas with lenslets. So very different detector technologies. They have different systematic control ranges, ranging from smaller beams to, say, rotating wave plates in Polar Bear's cases. So they're quite different in their ability to control systematics, which is important as we go after very faint signals. This is a map from 54 days of Polar Bear data showing high signal noise maps of the CMB anisotropy space. The science goals are similar for this experiment. With polarization, we want to do gravitational lensing, train neutrino masses, and by adding the lensing information from Polar Bear or SPT POL, we can improve the constraint from Planck by a factor of 1.7, going from a sigma of 170 milli-electron volts down to 100 milli-electron volts on the neutrino mass. In addition, we hope to get about a factor of 2 to 3 improvement on the gravity wave background with these experiments, going from limits of R less than 0.11 to R less than 0.03, 0.05 with these 2 experiments with the large scale of polarization data. And this in some sense illustrates what your question was, which is, for R of 0.02, the gravity wave signal is dominant over the residual lensing signal, but as you get to very low values of R, then you start to have to worry about what the lensing signal is on those large scales. And you'll have to start subtracting at that point. In addition, with the small beam, SPT POL will do a lot of cluster science. We expect to have about 1,000 clusters within our area of sky for SPT POL. And these will be lower mass clusters than we have in the current survey because we have lower noise with 4 times deeper maps. All these clusters will be in the dark energy survey footprint, so you can do studies between the dark energy survey and the SPT on these clusters, on these objects. What's been new in the last 6 months or so is that we've actually started to detect the lensing B modes for the first time. And doing lens reconstruction in polarization is quite different than what you do in temperature, where you have to average over many modes. In lensing, since there's no initial signal in B mode, if you measure an E mode map and you measure a B mode map, there's really a one-to-one correspondence that then tells you what the lensing potential is for one mode in that sky. So you can pretty much do a fitting process in this scheme. Now we'd like to do a cross-correlation for first detection to guard against systematics. So a natural question then is what you can use as a cross-correlation source for that lensing potential map. If you look at what would be correlated with a lensing kernel that peaks around a redshift of 2, and this is the lensing kernel in red, it's a fairly high redshift distribution, higher than, for instance, the NVSS radio source scala with peaks around a redshift of 1. However, it's quite well matched to the expected distribution of dusty galaxies. And if you use, say, the single SED model from Holodahl to predict the distribution of these dusty galaxies for observed counts, you calculate something like an 80% correlation between the distribution of dusty galaxies from, which can be measured with Herschel's fire, a satellite, and the lensing potential on the sky. So in doing this cross-correlation, we can use the Herschel map as our measurement of what that lensing satellite is. And since Herschel is a satellite and we're a ground experiment, they're very different experiments, and it's very unlikely to have any kind of instrumental effect that would contribute systematically to both experiments. And that's what we've done, both with SBT pole as well as polar bear. We took the E-mode map from SBT pole, a density map from Herschel's fire, and used that to predict what the B-mode map should be. And then we correlate that predicted B-mode map to our observed B-mode map and detect a signal. And we detect a signal with SBT pole at 7.7 sigma and with polar bear at 4.0 sigma. Polar bear has also done a separate analysis that's not a cross-correlation internally using CMB polarization led by Cheng here in the audience to get the detection at 4.2 sigma as well using CMB polarization alone of the lensing beam. So we're now actually seeing this polarized lensing signal for the first time. And you can put band powers on like CLBB and check whether they're consistent with your predictions of the standard cosmological model. And we find that they are. The dashed line is sort of the prediction for what this BB signal should be. And the data points are these band powers here. And we find consistency between different estimators and also different frequency ranges. They're all internally consistent. And when we do tests that should have no signal, like using a difference map instead of a co-added map for one of those correlation, we find results that are consistent with 0. And we see no evidence for a residual systematic error to just a ground pickup in one of our telescopes. It's worth noting, though, that these are only sensitive to B modes from lensing. So you wouldn't see B modes from, say, vector perturbations or primordial magnetic fields. And you also wouldn't see B modes from gravity waves, both because of this correlation, but also because we're probing very different angular scales. The gravity wave signal is, this L less than 100 band, where these band parts are starting at L 500 and above. To improve this, of course, there's the Simon's ray, which is going to dramatically expand the sky area that we're talking about. Up to something like 50% of the sky will be covered with the Simon's ray, which is an array of 3-meter telescopes in Chile. And that'll be an excellent data set for effectively covering that beach ball just with maps of the dark matter distribution on the sky. And you can do correlations between that with other of these large optical surveys like LSST that are going on in the southern hemisphere, as well as CCAT and other experiments. SBT3G is doing a slightly different scan trace. This is doing a large area, 50% of the sky. SBT3G is doing a much more focused sky, so you can effectively get a wedding cake kind of pattern between the two experiments. So now we're doing 6% of the sky instead of 50% of the sky, but down to lower noise levels. And actually the detectors in both cases are the sinuous wave, broadband sinuous wave antennas, shown here, coupled with lenses to the telescope. One of the main goals, as I mentioned, was neutrino mass. With the current error bars for SBT pole or polar bear being about 100 millivolts. For the CMB alone, you get constraints on the order of 50 millivolts from the Simon's ray or SBT3G. And these are the 1 and 2 sigma constraints from the CMB plus CMB lensing. As you can see, there's a degeneracy between the neutrino mass and the total matter density in the universe. Effectively, if you increase the matter density and increase the neutrino mass, you end up with the same amount of structure and the same amount of gravitational lensing on the sky. But it turns out this is a very nice other data point, which is Berkeley's oscillation data. And that actually has nearly perpendicular degeneracies. So if you add MS density to, say, the Simon's ray or SBT3G, you end up with a very tight constraint on your neutrino masses. And you actually can get down to neutrino mass constraints that are about 18 millivolts for the Simon's ray, are 22 milli-electron volts for SPT3G. So on the order of 20 milli-electron volts, which could then potentially discriminate between normal and invariant hierarchies, or actually make a detection of the neutrino mass at high significance. Certainly, if any of the current ideas about neutrino mass being an explanation for the discrepancy between galaxy cluster count with Planck, and which are needing 200 milli-electron volt neutrino masses, we could detect that 10 sigma or more. Of course,
is that affected by, so, for example, Planck gets, somewhat lower, it predicts a lower value of the Hubble parameter and a slightly different ratio of matter to dark energy, for example. So if there's some ideas on this that maybe you can resolve that by some extra radiation energy density or some photons, but does that affect what these neutrino limits would be?
For the CMB alone, it does not have a large impact. We did, lens for the SPT3D, we certainly did constraints with N effective, running, and all these other free parameters, and did not make a big difference at MNIT. I don't know what happens
this affects the
with
matter density
NSDAISY.
itself, right? So it's a little more serious.
This plot itself does not have a screen. I'm not 100% sure whether the degeneracy curve changes when you have N effective and all these other parameters, W, etc. in there. And you also get improvements on the number of relative species in the universe. So, for instance, SPT3G with their higher, smaller scales in the polarized power spectrum give you about a factor of 1.8 improvement on the constraints on effective you can get from Planck, and when you start having multiple parameters free. And I'll conclude there. SPT band pairs are still the best measurement of small-scale anisotropies between Ls of 1800 up to Ls of 10,000. Both on the primary and secondary CMB anisotropies. These are particularly interesting for looking at deviations from the standard cosmological model, both gravity waves, but also if you look at papers, neutrino mass, number of neutrino species, early dark energy, etc. And we've just had in the last 6 months the first detections of B modes in the CMB polarization. And in the next year, we should certainly have the first actual CLBBs, the power spectrum, as well as polarized power spectrum from these experiments. Start putting constraints both on inflation and structure growth, as well as particle physics. So, for instance, you can get constraints on decaying dark matter by looking at the temperature to polarized correlations in those CMB polarized power spectra. And I will conclude here and ask if there are any other questions.
So is there any degeneracy between early dark energy and something like N effective or neutrino mass?
There are degeneracies. Yes. Now, those N-effective constraints I used did have early dark energy in them at the same time, so that constraint included, and the improvement included those degeneracies. That was something like, I think we had early dark energy, W, running, N-effective, and new, and Y helium as well as parameters. So it was including a bunch of them at the same time for those sites.
So what kind of measurements could resolve those degeneracies? Is it like plate time measurements, low redshift measurements, for example, or would it have to be?
So certainly, like very quick Gaussian data, measurements of galaxy cluster bonuses. I mean, your standard set of other data sets. I think, but the geometry depth measurements are particularly powerful for measurements.
Christian, can you go back to the image, the zoom in resolution image? As you go
it's
from
like the very beginning?
Planck to, yeah, your scale. I'm a point source person, so.
You're not going to see planets. You're not going to see planets.
So I'm curious, have you now identified all of the point sources as galaxy clusters? Or
Wait,
galaxies, sorry.
The white ones?
Yeah, the bright ones are galaxies, but have you identified all those as radio sources?
No. Some of them are definitely not radio sources, right? Some of them are dusty galaxies. And we've seen, that they have dust-like spectrum. We see them with ALMA. We've seen, the individual stuff. Some of them, have Herschel data on them as well. So, I mean, certainly, All the very bright ones are radio galaxies, are consistent with radio galaxies. They have counterparts. Well, not all. Most of them have counterparts in radio surveys, but they all have falling spectra where they're brighter at low frequencies, dimmer at high frequencies, and are consistent with radio-like emission. I think on the order of 90% of them have correlations with the radio catalogs, and the remaining 10% do not.
Do you have any variability information from the survey?
We have some variability information. We have not looked at it. So typically we'll have a few months of data to 6 months of data on a patch, so you have that much variability information. And certainly the bright ones, our brightest sources, right, we can detect in a single hour observation. So depending on the brightness of the source also for how much information we have.
Other questions?
I have a really stupid one.
We don't accept it.
As somebody who's not from the field and does, it seems to me like it's a kind of a big deal observing the beam orbit. I don't think. And you're not. But you state that you've observed them. You're not showing how you observe them. How is it not the background? How is it not instrumental effect? Why do these people believe it? At least if I was becoming famous like this,
He did show actually.
I did show some of the null tests.
How do you show that this is real?
Talk to the guy next to you.
Sure, he's
question. I don't know.
You actually know, it's a
Okay.
good question. How do you know it's not an instrumental effect?
There were things around zero.
Where? Show me this.
So,
Later, fine. I thought it was more of a statement of a result.
No, they checked for that.
I saw this convolution.
Right there.
It's
Alright.
It's these
So,
like green points at the bottom.
the arguments against systematic would be first that they have the correlation, so your error would have to be correlated between your satellite and your ground base. And second of all,
Whoa, a sec. Now I'm going to give you a hard time because for the fun of it. Isn't your 7 sigma entirely driven by your correlation, and you wouldn't have it? So
but I'm saying that's the astrophysical correlation, but there's an instrumental correlation. If this was all due to an instrumental
yeah, but you can't
weirdness.
take credit for something that you already have used in order to establish significance, no? So if you want to convince me that you've seen it, then you have to give me something that was not used in determining the significance of the observation.
Sure. So I would say there's a logical argument, which is that if you had, say, ground pickup that was contributing polarization in the CMB, in our experiment, it would not correlate to that satellite, and therefore you wouldn't have seen it. The other argument would be that, so we used 150 gigahertz data. We've repeated the analysis with 90 gigahertz data. One of these plots, the green versus the black. And you can see the values are consistent when we use different detectors. We used a different estimator for the B modes. So changing the B mode map that we were correlating on, and that is the difference between, say, the black and the orange. And again, you get a consistent answer. We've done compared to temperature-derived lensing maps and get a consistent answer. We do null tests to look for systematic errors. So, for instance, doing a difference between either your E-mode map being a difference map, or either time-varying sources like the first half or second half, or sun-up, sun-down type things. And we don't see any signals in the correlation signal. And one of these null tests is shown in gray, but there are other ones that aren't shown. We've done other null tests of B-mode as well as E-mode. And if you do a curl type test where you don't expect to see a lens signal, you don't see any signal as well, whereas you might see some instrumental effects. And it's also true that this is the expected lensing signal. So we have seen lensing with temperature at high signal noise, and this is confirming that we see the same thing in polarization. So our signal noise on lensing with CMB is now 30 sigma. These are still a lower signal noise measurement of the total lensing power spectrum than what we're getting from temperature right now because of the data quality.
Okay, maybe one more question. I had a science question. If you, with the South Pole telescope, you've got a lot better resolution than you do with polar bear. What do you think about measuring the polarized SDF? Is that a possibility with SPT3G? And what would that tell us?
We looked at this for SPT3G, and it did not seem particularly possible or particularly interesting. The signal noise is not very good. I don't think it actually will be useful for SPT3G. some things people have talked about they're doing with like the clusters are measuring the cluster masses with CMB lensing, so using polarized lensing to measure the cluster masses, and we expect to get a couple % mass calibration in stacked analyses over the clusters, and that can help with cluster cosmology. And there are other ideas like looking for the kinetic genius Doge effect in the individual clusters to then recover the velocity fields. Then you have the velocity fields, 100 megaparsec scales that can tell you about, say, modified gravity type models, and put constraints on GR on those scales.
Okay, great. Well, there are no more questions. Let's thank Christian.
There you go. Sorry.
Okay, guys, so we should get started. I've been asked to remind everybody to sign in if you got pizza. So that's me asking you guys to sign if you got pizza. So today we have Christian Reichardt, who is a good friend and a close collaborator. Christian just reminded me I've known him actually since 2000. Actually, since 2000, when I came to Caltech. You were a junior, I think. Then. Christian's a remarkably productive scientist. He's been working for a relatively short amount of time. And you may not know this, but you've heard of the H-index, right? Mm-hmm. So the H-index was invented by our colleague here, Jorge Hirsch, who's a physics professor. H is after him. But I've recently, after looking at your publications on Google Scholar, come up with a new index called the age-index, which is what is your age relative to your age divided by your age.
That's a thing. Yeah.
That is a thing? What? You stole my idea.
And he did the imaginary.
Knew that satellite was. All right, so Christian has an age H-index of 1, basically, which is to say his H-index is over 30, and it's quite remarkable for such a young scholar in the field. And a lot of that's attributed to publications that he's led the work for. So in particular, the Akbar experiment, which is a PhD thesis. He got his PhD in 2008. That's right, 2008, working on the Akbar experiment, which until very recently had the. You guys missed my introduction of a statistic called the age index, which has already been co-opted by somebody else called the M index. Sorry. So Christian worked on the Akbar experiment.
Really good idea of how a hot plasma will evolve. As the universe expands, this plasma cools off, and different particle species can fall out of thermal equilibrium and survive at some relative particle abundance. Eventually, you cool down sufficiently that your protons and electrons combine to form neutral hydrogen, and the cross-section between free electrons versus neutral hydrogen is much higher, so now the photons can escape to free stream all the way to the observed state. So we get a snapshot of what the universe looks like a few 100,000 years after the Big Bang in the cosmic microwave background. This is our first image of the universe with electromagnetic radiation. In post-Planck era, you can learn more by studying polarization and smaller scale anisotropy to learn both about the initial conditions and about inflation thereby, as well as particle physics in the early universe, like decay in dark matter, neutrinos, and other extensions to the standard model. After the successful last scattering, you have a fairly neutral sea of hydrogen. But eventually, under gravity, these form the first stars and then the first galaxies, which produce UV and X-ray photons that should re-ionize the universe around it. And we know that by a redshift of 6 or so, the universe has re-ionized. But we don't really know what sources cause this reionization, what kind of stars, what kind of galaxies, and in fact, whether ordinary stars and galaxies are sufficient or whether there's something more exotic going on to drive the reionization process. This has, of course, been a major focus of 21 centimeter surveys. And we'd like to understand this in more detail. Structure continues to form in the ionized universe, and by studying this process, you can learn about dark matter, which is driving much of the structural growth. And this is forming under gravitational infall.
Experiment and deployed to the South Pole to deploy the hardware that he had worked on while he was a grad student for Akbar in 2005. So he's been to the South Pole. And yet returned to tell the tale about it. So today he's going to talk about an experiment that's currently going on at the South Pole, which is a sort of a competitor to polar bear, but also he's a collaborator on polar bear. So he's kind of in the catbird seat. He gets to work on 2 exciting experiments at the same time. And really what he's trying to do, as he says in this title, is probing fundamental physics, which is to say we're now probing what I consider the 4th most important particle in all of physics. George considers it the most important particle in physics, namely the neutrino mass. I mean, imagine if we didn't know the mass of the proton, of the electron. So Christian's going after probing aspects of fundamental physicists, heretofore reserved for our high energy colleagues who are now coming down because they smell pizza all the way from there. So it's a pleasure to have Christian. He's visiting today and tomorrow. We have spots for dinner available if people are interested, and lunch tomorrow. So please contact me if you're not on the list to meet with him. And otherwise, we're going to hear about this exciting new physics being probe by two of Christian's experimental projects.
Thank you, Brian. So as Brian said, I first went down to South Pole back in 2004, and I saw the foundations of the South Pole telescope starting to be built, the ice foundation for this. And I've been fortunate enough to work on it as my main focus while at UC Berkeley. During the course of the talk, I'll begin with a brief introduction and review of cosmology. Use this to motivate why we built the South Pole Telescope survey, as well as the polar bear surveys, and what we are finding in these surveys. From there, I'll focus in on the power spectrum of the cosmic microwave background, which is the normal way we have to interpret the data for these surveys, and talk about the features in the power spectrum and the cosmological interpretation thereof. And in particular, I'll be looking at what we can learn about inflation from the cosmic microwave background. And then I'll transition from data that we have to data that we're taking with CMB polarization, which can tell us both about inflation, but also about gravitational lensing of the cosmic microwave background, which gives us a handle on structure growth and the masses of neutrinos, as Brian mentioned. And I'll be talking about two experiments on Sky right now, SPT Pole and Polar Bear, and their planned successors, SPT 3G and the Simons Array. So the current model of cosmology right now is lambda CDM, lambda for a cosmological constant, CDM for cold dark matter. It's a fairly simple model in terms of number of parameters. You have 6 free parameters. Yet this model can actually explain all the observations we have today, ranging from the temperature and polarization anisotropies in the cosmic microwave background to the distribution and number counts of galaxies or galaxy clusters on the sky to measurements of the geometry of the universe, such as the luminosity distance relationship from supernova. At this point, we have, of course, thousands of data points constraining the 6-parameter model, so we have very tight constraints on our model parameters, pinpoint down a very tiny region of space, and we've learned that we live in a flat universe. The initial perturbations are nearly Gaussian and scale invariant, and the expansion of the universe is actually accelerating today, somewhat counterintuitive. And this points to one of the interesting aspects of this model. Although it's very simple, a lot of the major points of the model are still not very well understood. So 95% of the universe's energy density there is composed in the dark sector of dark matter and dark energy. And of course, their very name encapsulates how little we understand about what these objects actually are. In addition, we typically invoke a period of superluminal expansion early on, inflation, to address, for instance, the horizon problem. However, we don't know what causes this rapid expansion in the early universe. So all three of these are pointing to physics beyond the standard model that we could understand by studying cosmology. To understand how you might learn about these, it's useful to look at how the universe evolves in the standard model of cosmology. This is a pictorial representation of the history of the universe that you've likely seen before. And loosely speaking, you can break down the history into sort of 5 effects: inflation, the early hot plasma, reionization, the structure formation, and the accelerated expansion. What's nice is that my work relates to each one of these different effects on the following slides. I'll go through these in a little more detail and highlight some of the questions that remain about each epoch. We start off with inflation, in which you have this sort of e⁻⁶ expansion of the universe. This addresses problems ranging from the phase coherence of the CMB to the horizon problem to why we don't see magnetic monopoles. However, it's a big black box. We don't know what energy scale this physics comes into play, and we don't really know what is driving this rapid expansion, and whether there's any connection to the late time acceleration in the late time universe. After inflation, we have a